Good morning, everyone. My name is Xinmei Sun from School of Data Science in Fudan University. In the previous talk, Professor Yuan Yao introduced a theorem of differential inclusion for structural sparsity problem. In this tutorial, I will introduce some details and how they can be applied in the medical imaging field. I will take the Alzheimer's disease as an example. Today's talk contains three parts. In the first part, I will first introduce the structural sparsity problem in the medical imaging field and its related works. Then I will introduce for details how the differential inclusion can address this structural sparsity problem. Theoretically, I will show that this new method can recover the true signal set under weaker incoherence condition. However, this condition is practically unknown. So therefore, in the last section, I will introduce our recently proposed two approaches to control the false discovery rate. First, I will introduce the structural sparsity problem in the medical imaging field. In this tutorial, we mainly focus on the diagnosis problem. The diagnosis problem mainly focuses on two problems: the disease prediction and select disease-related features for better explainability. Formally speaking, given p covariance that can be expected from the image, we predict the disease status and select those disease-related features. For instance, in the Alzheimer's disease, as shown in the bottom left region, compared to the normal control, the patients can suffer from gray matter volume degeneration. And it's well known that the two-side hippocampus are responsible for memory and language processing. So therefore, it is expected that model can not only accurately predict the disease, but also can identify two-side hippocampus as disease-related regions. Besides, as we can also see, the lateral ventricular is enlarged, which can also be utilized for the disease prediction. And during gray matter volume preprocessing, some voxels surrounding the lateral ventricular can be mistakenly included as gray matter voxels. And we will elaborate how we can use this information for better prediction power. In total, there are three types of structural sparsities. The first one is pure sparsity, which means only a subset of features being selected is meaningful because they are disease related. And the spatial coherence means the, the similar degree of degeneration or brain activity between adjacent voxels, which is commonly believed in the neuroimaging analysis. And finally, because the disease-related gray matter voxels are generally atrophied. So the more degree of atrophy, the higher probability for the patient to be diseased. So there is a positive correlation between disease-related features with the label. And previously, there are several sparse learning methods in Alzheimer's disease. The first one is the lasso penalty with the lasso with the L1 penalty. And the elastic net with the L2 penalty can select more features which may be clustered together. And the graph net extends the elastic net to L2 penalty on the transformed vector by the graph difference operator. And the graph here is is defined over all the voxels, and each region and each connection is defined on over two adjacent voxels. And the generalized lasso replaced the L2 penalty with the L1 penalty for strict smoothness over the graph. And finally, the non-negative fused lasso additionally consider the positive constraint. Although these methods can perform good, they can suffer from the following limitations. The first is sparse learning method require the incoherence condition to hold in order to recover the true positives. However, this condition is not easy to satisfy. Secondly, existing methods equalize the disease prediction and the feature selection, which, however, may not be the same, and there is a gap between these two tasks. Specifically, take Alzheimer's disease as an example. There exists some enlarged voxels in addition to the degenerated gray matter voxels. These voxels, as we previously introduced, are introduced during the procedure of the preprocessing, hence are called procedural bias, and they account for the gap between the prediction and the lesion features selection. And they are also helpful for the because they are helpful for the disease prediction, but not belong to the lesion features. As shown, they are located around ventricular and also the space of the gyrus and other regions. And this is the result of our feature selection, and our method is called cvpr, which can relax the incoherence condition, and hence we can successfully and stably detect the two-side hippocampus. In comparison, other methods can either select redundant voxels or scatteredly distributed voxels, which are not explainable. And the selected feature of our new method is composed of two parts. And the first part is the lesion features, and the second part is the procedural bias, which respectively refer to the degenerated and enlarged voxels. By additionally considering the procedural bias, our method can improve over other methods in terms of disease prediction. In summary, our method can simultaneously achieve more accurate disease prediction and more reasonable lesion feature selection. In the next section, I will theoretically explain how do we overcome these limitations and achieve this promising result. We consider recovering the true signal beta star from n linear noisy transformations, and the D denotes the design matrix. The structural sparsity is defined as uh, it defines as the sparsity constraint on the gamma star, uh, the which is the transformed vector of the beta star. Here, the D is the transformation matrix, and different choices of D correspond to different applications. For instance, when D equals to identity matrix, it is the pure sparsity problem. And when the columns of D form the wavelet basis, the problem did correspond to the wavelet smoothing problem. And the D can also denote to the total variation matrix in image noising. And other choices of D not included here contain trend filtering, change point detection, and so on. And the question is how to recover the sparse pattern of the gamma star and also estimate the true values of the signal, which are called respectively the sparsity and consistency problems. And there is a large literature on this problem. And the most popular one is the generalized Nassau, and we call it Gen Nassau for simplicity. And this is proposed by Tipshirani and Jonathan Taylor. Previously, it has been studied as total variation in image denoising, fused Nassau, and the pure sparsity problem. There are mainly two problems of the generalized Nassau. The first one is the computational issue that one has to run several lambda for optimization and in order to obtain the whole solution path. And this is computational expensive. And also the most key one problem is the incoherence condition, which is also called the irrepresentable condition. And it is hard to satisfy because of the multi-collinearity problem in the high dimensional scenario. And so to address these two limitations, our proposal is like this. We first reformulate this problem by introducing another parameter called gamma, which is constrained to be equal to d beta star. And we relax this linear constraint using a variable splitting term between the d beta and gamma. And the value of nu here measures the degree of freedom of the beta from the gamma. And we then propose the following differential inclusion, which generates a whole regularization solution path of beta and gamma, as we will show later. And this differential inclusion is composed of two parts, the update of beta and update of the gamma. And at each time step, the beta can be solved directly. And for gamma, we introduce another parameter called rho, which is denotes as the subgradient of absolute function of the gamma, which is illustrated here. And it is differentiable except for the 0 point when it has subgradient belongs to -1 to 1. So the rho equals to 1 or -1 respectively when gamma is selected to be positive and negative. And as iterates starting from 0, the beta undergoes a gradient descent flow, and it finally reaches to the 1 or -1, which means implies the gamma to be selected. So the T here can be regarded as the regularization solution path, because as T increases, more and more variables will be selected to be non-zeros. Besides, we can make the penalty function strongly convex by introducing another L2 term with the damping parameter kappa, and it can approximate the original L1 penalty as kappa increases to infinity. And so we can also calculate the subgradient of the gamma of the L1 penalty passes the L2 penalty. So it is it is called at the CT, and the gamma T can essentially be obtained from the CT as illustrated, because when the CT is greater than 1, for example, the gamma T to the K to the kappa can be obtained by the CT -1. Okay, and in the region when the ZT is less than 1, it is like a mirror. So it is the gamma can be similarly solved. So because the gamma can be inversely solved from the CT, we can have the an easier way of discretization of this differential inclusion, and we call it split LBI. It is the abbreviation of the split linearized Brackman iteration. And this is our solution path. As shown, the split LBI is nearly piecewise constant. And as iterates, more variables will be selected to be non-zeros. Note that different from common optimization algorithm, which only focus on the convergence of the solution at the final step, our split LBI can generate a whole regularization solution path as iterates, in which the signal are picked up first, followed by the noise variables. Therefore, instead of the final step, which can overfit the noise, we should adopt an early stopping mechanism so that only the signal is picked up. Therefore, a natural question to guarantee this nice property is, do the early selected features belong to the true signal set? And here is the high-level iteration regarding our theoretical result. And we denote the oracle subspace as the space expanded by the true signal set, and we denote its complementary space of as the overfitting subspace. And the irrepresentable condition, which implies the orthogonality between these two subspaces, ensures that loss function decay first from 0 to on the oracle subspace first, and to pick up more and more signals until to the saddle point which is unique because of the restricted strongly convex. And this settle point is actually correspond to the oracle estimator, which pick up all the signals. And after that, the model start to pick up the noise variable, so it is start to track on the overfitting subspace. So we should adopt an early stopping mechanism after picking up the signals at the settle point. Recall that we previously introduced a variable splitting term which has a hyperparameter nu, and this the larger value of nu can in our variable splitting can relax the linear constraint between the d beta and gamma. Hence, it lifts the original parameter space into a higher space, making it easier for the irrepresentable condition to hold. Broadly speaking, our irrepresentable condition, namely the IRR nu, is dependent on nu, and this assumption means it is less than 1. To see why this irrepresentable condition is easier to satisfy when nu increases, we show that essentially larger value of nu can make these two subspaces be more orthogonal. That is, the angle increases to 90 degree when the nu goes to infinity. So formally speaking, when nu converges to 0, our IRR nu reduces to the IC condition of the generalized Lasso. And with larger value of nu, our condition is less than the IC condition. And we can theoretically prove that it converges to 0 if only if the kernel space of X belongs to the kernel space of D restricted on the true signal set. And the later condition turns out is equivalent to the strong convexity condition, which is the assumption 2. Besides, note that because of the variable splitting term, the beta t is not sparse, so we can hence project the beta on the subspace expanded by the support set of the gamma at each step to return another solution called tilde beta t. So this is a sparse estimator. And under the previous two assumptions, we can have the following theoretical result. We can first guarantee the no false positive guarantee that uh, uh, the early selected features belong to the true signal set. And when the algorithm stop at the top bar, we can recover the sign of the true signals. And also we can have the minimum with the minimax optimal result in terms of L2 error. We demonstrate the effectiveness of our variable splitting in terms of the AUC on the synthetic data set. The AUC measures the goodness of feature selection in the solution path because the larger value of the AUC means early selection of the true signals. When nu increases, we can see that our split LBI can outperform the general Lasso in terms of AUC. And also the AUC increases and as nu increases. And this can be explained by the left figure of the IRR condition that when nu equals to 0, our irrepresentable condition equals the IC value and it is larger than 1. So both assumptions are not satisfied. But as nu increases, our IR nu can decrease continuously and finally be less than 1. So this means our condition can be easier to satisfy when the nu increases. In addition to the model selection consistency, the relaxation of the linear constraint endows The dense parameter beta with more degree of freedom to capture other variables or other signals that are related to the response variable. Therefore, our method can have better prediction power since we can capture the procedural bias. In summary, we propose a novel iterative algorithm which can uh, generate a whole regularization solution path via a differential inclusion and with a simple discretization algorithm. And as iterates, more and more features will be selected, and other selected features belong to the true signal set. And the variable splitting term can, on the other hand, enables to explore beyond the sparsity. However, practically the incoherence condition is not known. So therefore, this inspires us to control the false discovery rate. In the next section, we will introduce two approaches to control the FDR, respectively from the wrapper method called speed knockoff and the perspective of empirical bias. We first review the knockoff method, which is proposed by the Emil Candice and Rina Barbers. The FDR is defined as expected a ratio of false discoveries among all discoveries. And the knockout consider the FDR control in this, for the pure sparsity problem. And the Q is the preset desire level, for example, the 0.1. And the high level of knockoff is like this. For each feature xj, we create a copy called xj tilde as a control. And the noise variable, because the noise variable is homogeneous, and this can have a good property we will mention later. And then we implement the black box algorithm to calculate the Cj and Z tilde j, which respectively measure the effect of xj on the y and xj tilde on the y. And for each feature, we after that we calculate comparison score, namely the wj. And if the zj is larger than the z tilde j, which means the original feature has larger effect, it is positive. And if it is negative, means the original feature has less effect than its copy. So for each non-null feature, the wj can be large positive because the original feature has tends uh, generally has a larger effect than its copy. But for the null feature, we have the exchangeability property because of the homogeneous of the noise variable, which means the distribution of the W is unchanged after we swap each subset of features with their copies. In this regard, the W of each feature has equal probability to be positive and negative. So this means the ZJ is comparable with its copy. As shown, the calculate W for non-null features are located on the positive and large region. Well, for null features that are marked by the black dots, they are symmetrically distributed across two regions. After that, the knockout selects those features with large positive and a starting time TQ, which denotes the minimum time point in which our estimated FDR can be lower than Q. Theoretically, it can be proved that the FDR is less than Q, and but in a scenario of structural sparsity, when we consider the FDR control of the gamma, if the D has full column rank, we can inversely solve the gamma from the beta and construct the copy following the standard knockout procedure. But this is intractable when D is not full column rank. So therefore, we formulate this problem in the joint beta and gamma space with heterogeneous noise. So we similarly construct the copy of each x gamma uh, and this copy is named x tilde gamma. Similarly, we can calculate the dj and d tilde j respectively as the largest regularization hyperparameter for the gamma j and the gamma tilde j to be non-zero. But due to the heterogeneous noise, we don't have the exchangeability property as shown in this figure that for the null features, um, the Wj tends to have larger magnitude and it is more likely for the null feature to have to be negative than to be positive. To resolve these problems and to ensure the exchangeability property, and we propose the truncation solution that we truncate the magnitude when the d tilde j is greater, and also the probability of d tilde j to be greater than dj when the sign of the gamma and the gamma tilde is not the same. And in this regard, if we look at the KKT condition, um, these are the KKT condition for the gamma and the gamma tilde to be non-zero um, for the generalized Nassau. And as we can see, the gamma, the KKT condition for gamma is only dependent on of the beta lambda, which is determined by the Cassi. Of which is a function of the noise variable, and the KKT condition for the gamma tilde is come up with an additional term called zeta. And when zeta is less than 0, it means the gamma will be selected first earlier than the gamma tilde. So this means condition on the zeta, the W has the probability of W is be positive is equal to the equal to the event when the theta j is negative. And we have the properties of the if we solely look at the zeta, it is unbiased to 0 and it is dependent to each other. But when conditioned on zeta, these two properties do not hold, which means the Wj of the null statistics are dependent to each other. To address these problems, inspired by the KKT condition, we split the dataset into two parts, the D1 and D2. The D1 is responsible for calculating the beta lambda, and D2, from D2, we can obtain the DJ and D tilde J. And in this regard, the data is no longer dependent on the zeta because the Cassi is no longer dependent on the zeta because they are uh, calculated from two different data sets. And in this regard, we can equalize the event of the positive of the Wj to the event of the negative of the zeta j. And so we can have the unbiased property of the zeta and independence among the events of the positive of the null statistics of the Wj. So this means for the null feature, we have the W has equal probability to be positive or negative. And we can have the following theoretical result to bound FDR control, and we consider the three settings of structural sparsity for the identity matrix when diffuse Nassau and concatenation of these two matrices. And in all settings, we can successfully control the FDR under the desired level. We also applied our method on Alzheimer's disease to select the disease-related regions and connections over brain regions in Alzheimer's disease. And each connection involves two adjacent regions with different degree of degeneration. We mark the selected region as red and the selected connection as bold edges. As shown, the old connections involve the hippocampus, which is also selected in the selected regions. And also we can additionally select the medial temporal lobe, and which is also found to be early damaged region for Alzheimer's disease. However, the knockoff requires n greater than the n plus sp, which is not satisfied in the high-dimensional scenario, and besides the power is limited due to the multicollinearity problem in high-dimensional setting. And this can be illustrated from the following observation that we compare our split LBI on the V8 and V4 dataset. In the V8 dataset, each voxel has 8 cubic millimeters, and so it only has 2,527 voxels. But for V4 dataset, we have 20,000 voxels. But even with more voxels, the performance dropped from 90 to 89, and this because we have the more serious multicollinearity problem. But in comparison, we propose a new empirical Bayesian method called FDR smoothing, heterogeneous smoothing that can select the early degenerated regions that missed by the G-split LBI, and also identify the procedural bias exactly surrounding the ventricular, and this result is very promising. So in the next part, I will introduce our empirical Bayesian method to alleviate the multicollinearity problem and improve the feature selection utility. We first review the hypothesis testing method, and the classical is two simple t-test, and we can calculate the p-value of each feature, and we can also use the BH procedure to finally control the FDR. But as the BH procedure assumed independence among all features, it is too conservative in feature selection. So to address this problem, the FROM proposed a local FDR, and which is composed of the two groups and of the density function F0z and the F1z. The F0z is the PDF of the null group, and the F1z is the non-null group. And the P0 denotes the prior of for each feature to be null. And we can calculate the posterior of the FDR given each feature z, and we can use the central matching to estimate the F0z, P0, and also use the kernel density to estimate the FZ. But the limitation is the ignorance of the spatial coherence prior. So the Tennessee in 2014 proposed the FDR smoothing that replaces the unified prior to the prior for each feature, and which incorporates the parameter beta, and we can implement the Fuse-Nassau penalty over the beta. And the loss function L beta here is the negative log likelihood. But the procedural bias and lesions are heterogeneous in terms that the procedural bias is enlarged and the lesions are atrophied, and they have different degree of spatial coherence. For instance, the lesions are more clustered than the procedural bias. They are clustered surrounding the ventricular. And to model the heterogeneous smoothing, we define three graphs, the graph over enlarged voxels, and also the graph over the lesion features, atrophied voxels, and the biparate graph between enlarged and atrophied voxels. As they have different degree of smoothing, we implement the L1 penalty with different hyperparameters. Since the loss function is not convex, we introduce a binary hidden variable s, in which s equals to 1 if it is generated from the non-null group. And we define the loss functions over the parameter beta and the hidden variable s, and which can be optimized by the EM algorithm. After optimization, we calculate the posterior probability for the feature to be null, and we then select those features with posterior probability of the null to be less than some threshold value gamma. For the application on Alzheimer's disease with 20,000 features, but only with hundreds of samples, our method can outperform others in terms of prediction power. Moreover, our method can successfully identify more explainable features. And besides, we also calculate the stability, which is measured by the ratio of overlapped selected features over the all selected features across tenfold cross validation. The higher the MDC implies the more stability uh, of the model. As shown, our method is the most stable one in terms of feature selection. Okay, this is the end of my talk. Thanks for listening, and I am looking forward to the questions.